Today, Jaemin is going to talk to us about path dependent types with path equality in joint work with, not sure if I try to pronounce it, Jiang Park and Sukyung Ju with Zundu. So let's begin.
Hi, I'm Jaemin from Thai. My colleague Jiang Park and my advisor Theorem and I experienced some difficulties while implementing JavaScript static analyzer named SAFE in Scala. So today I'll talk about the motivation to start this research and how we formalize thought with path equality to solve the problem. SAFE uses abstract interpretation to analyze programs. Abstract interpretation automatically verifies certain properties of programs. Programs are interpreted on abstract domains rather than concrete domains. Abstract domains contain abstract values, which are abstraction of real values. So every abstract domain has a common signature, even though they might correspond to different concrete domains. In SAFE, there exists abstract domain for number, string, boolean, and so on. So all of them has abstraction function alpha and concretization function gamma. So we can model this common structure as a trait named epsilon. And we can define an abstract domain for a specific concrete domain by extending epsilon with some domain-specific operators like integer addition and string concatenation. And there are multiple ways to implement an abstract element for the same concrete domain. So user must choose an appropriate implementation depending on the properties they want to verify. So let's see how can we implement abstract domain in Scala by using its features. We define trait epsilon with type parameter v. V is its corresponding concrete domain. And it has abstract type member lm. Lm is its type of its abstract element. Instead of defining lm as a trait or a class, we distinguish its implementation into the another trait named lm input. Two definitions are coupled by using upper bound and self-type. Also, we declare the signature of alpha and gamma function. Now, we'll define an abstract domain for a specific concrete domain. Here is integer. We define int_dom by extending epsilon with type argument integer. Also, it contains some integer-specific operators like addition and multiplication. Now let's consider different abstract integer domains named A and B. They have the same signature but different implementation of abstract elements. So it's clear that we must not apply operators on abstract elements from the different abstract domains. The Scala type system can prevent such things happen by accident. In this code, variable A is an element of domain A, and variable B is element of domain B. Since addition method takes an abstract element from the same domain as an argument, type checking A plus A succeeds, but A plus B will reject it correctly. So now we hope to do something more. Our goal is defining an abstract domain combinator which combines two or more abstract domains to construct a new abstract domain. Pair domain combinator can be one example. We define pair dom, which takes two abstract domains as parameters. It constructs new abstract domain whose element is a pair of elements from two given domains. Also, its elements has the method named left and right for the projection. So note that the bezier left has the return type dom_L.length. Now we define P a pair of A and B by extending pair boundary. Then P.dom_L and A are exactly same domain. It means P.dom_L.length and A.length denote the exactly same type. However, we cannot use that fact. So let's see. Here, variable P is an element of domain P. So we can use P.left as an element of P.dom_L, but not of A. Since the Scala type system does not track that A and P.length are the same path, so two types, A.length and P.dom_L do not conform. So type checking A plus P.left fails, which we do not desire. So therefore, P and in general, every abstract domain combinator are useless in most cases because their abstract elements cannot be used as elements of their original domains. Therefore, to solve the problem, we suggest a new dot variant named pi dot. We defined pi dot based on mu dot of Amin and others. Pi dot tracked the path equality and used the information during the type checking. We proved the normalization property and type soundness of pi dot. This is the syntax of mu dot. Here, a type can be a record type or a type selection on a variable. A record can contain time members and methods, but not fields. So first, to simplify the type system, we just remove method from record. However, we still need a way to bind a variable. We simply add a let binding to language. And also, while we try to add field to record, we faced a subtle problem. Online method, since field should be initialized during record creation, there is some order between field. It means if self-reference is available, then the body of the field might refer to uninitialized field. So dealing with this problem is an interesting topic, but it will add unnecessary complexity to our language. So we decided to drop self-reference from record. So now we can easily add field and path to our language. A path is a let-bound variable or field selection on a path. And type selection can be done on path rather than just a variable. So this is the complete syntax of pi dot. As I mentioned, it contains field, path, and type selection on a path. To track the path equality, we introduce path environment. Path environment is a partition of path. So if two paths are equal, then two paths belongs to the same set. Here, this code introduces two paths, x and x sub f, and they are different. So at this point, the path environment should contain two singleton sets of x and x sub f respectively. And now, under the previous path environment, we bind such term to variable y. It means that path environment should be updated to include newly created paths, which are y, y.f0, y.f1, y.f1.e, and y.f2. Since a let binding is only placed where new paths are created, the other type rules are trivial, but we must change the type rules for let binding to update path environment. The type rule uses two helper functions named implies and expand. The implies function collects the newly created path and path whom they are equal to. and the expand function add path to path environment based on the result of the implies function. So let's see how two functions work with concrete examples. First, the implies function works on the binding term inductively. The important point is that the implies function does not know the name of the binding variable. So first, it destructs the record to its fields. It collects path equality related to its fields and sums them up. The first case is F0. Here, since x is assigned to F0, x and F0 are equal paths. However, at the top of the derivation tree, implies function does not know the name of the field. So at first, it simply says that some path is equal to x. And then, when it finds the name of the field, it says some path end with F0 is equal to x. The second case is record creation. In this case, with more inductive steps. At first, some path is equal to x of f, and then the implies function prepend the field name. So some path ends with e is equal to x of f. And then the implies function for record creation concatenates every result from its field and add the record itself at the end of the list. So it's here. However, the record itself is not equal to any existing path, so it is null to denote that. It means some path is created, but it is not equal to any existing path. And finally, the implies function adds and prepend the field name F1. The last case is this, F2. So in here, that binding is assigned to the field. The implies function simply says that there is no equal path for left binding and field selection on non-path terms. So actually, in Python, since Python is so simple, the type system is able to track every path equality. However, in reality, finding every path equality from general terms, including method invocation, cannot be complete. So we decided to design our language to ignore such cases and deal with only record creation and path. It corresponds to variable aliasing and passing path as class arguments in Scala. Finally, the implies function collects the result of the field and concatenates them and add the record itself at the end of the list. Now it's time to see the expand function. It takes the current path environment, the left binding variable, and the result of the implies function as argument, and calls itself recursively. It adds path to path environment sequentially from the end of the list. If a path is not equal to any existing path, it just simply adds the singleton set to the path environment. So here, a singleton set containing y is added to path environment. Same for y.f2 and y.f1. And when a path is equal to some another existing path, then the expand function find the proper set from the path environment and add the path to the set. So here, y is prepended to f1.e, and y.f1.e goes into the set containing x of f. In the last case, the expand function should add y.f0, which is equal to x. So first, it adds y.f0 into the set containing x. But it's not enough. Since x.f exists, it needs to add y.f0.f to the set containing x.f as well. So as a result, two sets are updated. Finally, it successfully updated path environment as we desired. Then where the type system uses path equality during the type checking? The answer is subtype comparison. Here, if when the type selection, the same type selection on two equal paths are compared, then two types are equal. Also, in general, type system use the bound of any equal path during the subtype comparison. So I showed all of Python, and there is one more thing to mention. We find a way to implement abstract domain combinator without adding path equality to the type system. So the solution is using singleton types. We can force the path equality by using singleton types. Here, in this version, PairDom has two more additional type parameters, which are type of abstract domains. The types are constrained to be singleton types. Now we can pass eta type as type arguments to force that type of p.domain to become eta type. It means a.lm and p.domain.lm are the exactly same type. So a plus p.left can be type checked, and now any abstract domain combinators can work successfully. So let's compare two solutions. First, if we add path equality checking to the language, then it results more intuitive behavior, at least for us who implement static analyzer. And also, it allows user to write code more concisely without adding additional type parameter or singleton types. However, path equality checking will always reveal the implementation, while user can control the level of abstraction under the original type system. Also, path equality checking will add considerable overhead to the type checker. In summary, path equality can increase the expressivity of language. For example, we can implement abstract domain combinator easily. Therefore, we define Python, which formalizes path equality and prove its soundness. Thank you.
So we have time for a few questions. I would start. So you have shown previously a comparison of the two approaches, singleton types are existing in Scala and path equality. So my two questions are, you have your soundness proofs, and singleton types are existing in Scala and not formalized. Do you think your proofs would be a first step toward adding singleton types to the formalism? Do you think that it would be helpful? And the second question is, do you think that there would be a way to combine these two approaches somehow for Scala?
Can you say the first question again?
So the first question is about singleton types are not yet formalized in Dot. Do you think your work, your proofs would help in that formalization effort?
I'm not so sure because I think two features are not so tightly related. So for the formalization of singleton type, formalization of path equality will not be so helpful, but because I did not try it, I'm not sure. And for the second question, to combine this approach, that's an interesting question. Maybe we can try that, but I'm not sure that what will be the use case for combining both approaches, because if adding path equality does not require singleton types to force path equality, and singleton types make type checker to know path equality without track all the path equality by itself. So I think two approaches are quite opposite. So I'm not sure there is a use case or not.
We have two questions from back in the audience.
Okay. I wonder how to implement this expand function. It looks a bit like some search and prologue where you get something that is said, and based on this information, extend the knowledge of the quality. Do you use any tool like prologue or data log, or just implement
I only formalized the type system, but I did not implement it to real compiler. So there is no real way to implement it. Yeah.
So current Scala, this singleton type is only used to force the type inference to infer singleton types, but it's actually not necessary. In your example, you don't need the singleton type, right? So if you remove this with singleton, it will still work.
If we remove this singleton, then type inference cannot infer this as a singleton type, but we
actually does infer it if A is an object.
That's also right. But actually, I have another reason to add this singleton annotation, because if we do not force it to be singleton, then we can explicitly pass the not singleton type to here, then the pathway quality will not be checked. So I think it's necessary.
It's not necessary.
Yeah,
it's not going to break anything if you say something that's
okay, it's better, I think. I think you're right.
Brad, for the last question?
Yeah, just a quick question. So I know you mentioned that there are some features in Dot that you sort of have to, get rid of, so to simplify things a little bit, so that you can do this. Do you have a sense for how scalable the proof that you have is to full Dot? Even I know it's a hard question, right? Just in general terms, can you
actually? I removed many features, including method and even self-reference, so it's very far away from real Dot, and I think adding all those features to this type system will make proof much harder, and I'm not so this simple type system and its proof is so scalable, so maybe focus for full Dot we need another approach to proof. Yeah.
Thank you very much.
Okay, let's thank our speaker again.